Hi, everyone. Welcome to our short lecture for week 7 on conditional probability. So I wanted to have this lecture for you to watch before class, hopefully. That way we're all on board with this rather tricky concept of conditional probability, so we can really get started on Wednesday. Okay, so let's go. I think it's always worth going over what we saw last Wednesday. So remember, we saw 5 rules of probability theory. And from these 5 rules, we build our system of inductive logic, or we build the theory of mathematical probability. And we want these rules to be as simple as possible, right? We want to assume the less possible, right? These rules are assumptions. And these were the 5 that we came up with. So it's not all of them, but we can already do quite a bit with them. So the first rule is that tautologies get assigned probability 1. So remember, the tautologies are always true. And so statements that are always true, we want to assign the highest possible probability, which is 1. And similarly, self-contradictions, which are statements that are always false, we want to assign those the lowest possible probability, which is probability 0. So tautology is always true, maximum probability, self-contradictions, always false, lowest probability. Okay, so we're bounded in our probability between 0 and 1. The third rule states that equivalent statements get assigned the same probability, right? So if 2 statements A and B are logically equivalent, then the probability of A is equal to the probability of B. So what this rule is saying is, well, if 2 statements are just saying the same thing, then we want to assign them the same probability. Seems pretty reasonable. The fourth rule states that if 2 statements A and B are mutually exclusive, then the probability of A or B is equal to a probability of A plus the probability of B. So remember that if we have the sample space, the omega, and we have A over here and B over here, and they don't intersect, that means they're mutually exclusive. Remember, mutually exclusive means that they can't both be true at the same time. And the probability of A happening or B happening is the same as the probability of A happening plus the probability of B happening. And the last rule we saw is that if 2 statements A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. Right, so the probability of me drinking this glass of water is independent from the probability of Biden, right? Let's just use the same example of Biden being reelected president, right? And so if you want to take the probability of me drinking the glass of water in the next 5 minutes and Biden being reelected president, you just take your probabilities of those and you multiply them. Okay, so what about conditional probabilities? So we saw this example where, suppose I roll a 6-sided die that's fair right? I could roll it over here and you wouldn't be able to see it, right? Because I'm on video. But I tell you that it's an even number. Now you might ask, well, what's a probability that it's also a high number? Meaning that it's either a 4, a 5, or a 6. Right? So here I gave you information. I told you it's either a 2, a 4, or a 6 by telling you it's even, right? And I'm not tricking you as I usually do. It's really a 2, a 4, or a 6. And now I ask you, well, what's a probability that's also a high number? And so it's 2/3. And we got a bunch of different responses in class, right? So the intuitions aren't super clear. And here's where probability can help us. And the intuition, here's a visual description of why it's 2/3. So we have 6 total possibilities, right? 1, 2, 3, 4, 5, 6. And by me giving you information that it's even, I restricted the possibilities to this red, to the color red over here. So it's either a 2, a 4, or a 6. So before you had 6 possibilities, and now you only have 3 more. And now I'm asking you, well, what's a probability that's also a high number, right? And here you just have to say, well, is 2 a high number? No. Is 4 a high number? Yes. Is 6 a high number? Yes. Okay, so you have 2 yeses and 1 no, and so it's 2 out of 3, right? And the yeses here are shaded in blue. Good. So just to emphasize this, it's true that 5 is a high number, right? But I told you that it's going to be even, so you don't even need to consider 5 in this equation. Okay, so let's look at some more intuitive diagram after I go over some of the definitions again. So remember that we write that the probability of A given B with this dash over here, and that's a conditional probability. Another way to say it is this is the probability of A conditional on B happening. And we define it formally with as the probability of A and B happening over the probability of B. And one thing you might ask here is like, well, the probability of A given B sounds very much like the probability of A and B. But we're going to see later with some diagrams that this isn't the case. It's the probability of A and B over probability of B because you're assuming that B happens. So I recommend you to memorize this definition, and with time, the understanding will come if it's still fuzzy. But hopefully after this lecture, it will be less fuzzy. But just note a little caveat here that we're dividing by the probability of B. So if the probability of B is equal to 0, then this conditional probability is undefined. It's not that it doesn't exist. It's not that it's 0. It's undefined. Okay, so here we have the omega, which is a sample space again, and we have our definition of a conditional probability. And so I'll give you a little time, right? You might pause this video and look and see and try to think, okay, how can I draw the probability of A given B? Okay, if you pause and you thought about it, so let's go through it. So remember that I'm not asking you just what the probability of A and B is, right? That's the part that's shaded red over here. And in the example of the 6-sided die, I wasn't asking you, what's the probability of it landing of it landing high and even? Because that would be 2 over 6, not 2 over 3. What I was asking was, given the information that you know that it landed on an even number, what's the probability that it's a high number? And that's slightly different here. Here we have new information, and so you're restricting your space of possibilities. So it's not just this. Step 1 is to say, well, we're given B, right? So that's what we know happened. We know that it's going to be a case where B happened. So we actually don't even care about the broader sample space yet. What we care is, well, what's the probability of A and B happening given that B happens? Right? And so the A and B, remember, is this red part. So what we care about is, right, we can even forget about the rest of A now, is the ratio between this red part over here over the blue part. And so that's a conditional probability, is you have the information that B happens. So you can forget about all the other possibilities because you know that B happened, and then ask, what's the probability that A and B happened? And so you're restricting the possibility space because you know new information. And as we're going to see, this conditional probability is going to be very useful for us to update our beliefs in a rational way. But that will only come in next class. Okay, right. So the probability of A and B is this red part over here, and the probability of B is just the whole circle. Good. So let's just quickly use the definitions that we learned to see how it's different. So it's not just the probability of high and even; it's the probability of high given that it was even. And so maybe you should take a moment to do this on your own, and you can pause the video. But here, so it's just probability of high given even is equal to the probability of high and even over the probability that the die landed even, right? As I said, high and even is 2/6, right? Because this is, you have no new information. You just know high and even. So high and even is only 4 and 6, but that's over all the possibilities. And the probability that it's even is 3, right? So it's this whole red. So it's 3 outcomes out of the 6. And if you work this out, it's just 2 out of 3. Okay, good. So let's go over one more example. So I'm going to try to, I hope my face over here on the screen doesn't disturb. So the probability that it rains in California, let's say that it's 10%. So probability of rain is equal to 0.1. So I put not exactly to scale. So rain happening in California, rain is this circle with the little r. And the probability that it's less than 5 degrees Celsius in California, let's say that it's 1%. So it's 0.01. But these aren't the real probabilities, but just to give you an intuitive example. So here I put the statement that it's less than 5 degrees Celsius as the circle C, which is mostly in R, but there, you see that there's a little part that leaves. And suppose you also know that the probability that it rains and that it's less than 5 degrees is like 0.8%. So it's 0.008 of probability. So over here, I'll just color it. Right? So where is it going to be? Probably of rain and less than 5 degrees. It's going to be this, right? It's over here, not including this little part over here. But now if I say, well, what's the probability that it's less than 5 degrees given that it rains? So here you can say, well, I know that it rains. So I know that R happens. So I know that I'm in this circle, right? You know that you're in the circle of R. So you could forget about all the rest. And the question that we're asking is, well, what's the probability that it's less than 5 degrees? And here, so now we're asking, well, what's the probability of this? So apologies that it's not perfect, right? But of this blue shaded part compared to the purple shaded part. And if you forget the rest of the sample space, you'll notice that it's much larger. So the intuition is, well, when it rains, usually it's colder. And if you know that it rains, then you're more likely to believe that it's going to be cold, right? So here we just use the definitions, which is probability of rain and less than 5 degrees over the probability that it rains. So, right, 0.1 and 0.08, and that is 0.08. And this is 8%. So the probability that it rains, the probability that's less than 5 degrees given that it rains is quite high now. It's 8% compared to the probability that it rains and that it's less than 5 degrees, which is 0.8%, right? Because of this new information that it rains. So just to recapitulate, if you know the information that it rains, if you know that it's going to rain, right, then it will give you a much higher degree of belief that it's going to be less than 5 degrees. And these are the sorts of things that conditional probability allow us to do. And on next week, well, this week, on Wednesday, we're going to see something called the Bayes theorem, which is the rational way of updating our beliefs. But I hope this lecture helped solidify the idea of conditional probability. And just a couple last points. So is the probability of A given B the same as the probability of B given A? And no. So it's true that the probability of A and B is equal to the probability of B and A. It's not true that the probability of A given B is equal to the probability of B given A. So you can prove this, and I urge you to try to do this at home. And if you want more information, I recommend you going to this website by Jonathan Weisberg. And there are some very intuitive examples, and it's a great read if you're interested in learning more in depth and more about conditional probability. Great. I hope this helped.